Hey guys, welcome to your Chapter 5 notes, or your Chapter 5 Lesson 2 notes on direct variation. By the end of the day, you'll be able to write and graph an equation of a direct variation. Our key idea is all about ratios. So if you have the ratio, remember that's like rational numbers. A ratio is, anything to anything else. It's a fraction. All fractions are ratios, okay? So if you have the ratio of two variables, and that's constant, then we say the variables vary directly. They vary directly. And you know what? Every time we have a direct variation, I'm going to make that blue. So I'm going to go ahead and just make this blue. The variables vary directly. And what a direct variation looks like is you have some independent variable y, and then you multiply that by some constant k, and then you multiply that times x. So you get y equals k times x. So remember this forever. This is your key idea of the day. Direct variation is y equals k times x. You might also see it expressed, so this is my favorite way to express it. You might also see a direct variation where they divide both sides by x, okay, and they say y over x equals k. That's also fine. This also helps you see that it's a ratio. That k is something over something else. So there you go. Whatever way you prefer, that's great. K has a special name. We call him the constant of variation because he tells you at what rate the variables are changing. Constant of variation. Okay, so I'll ask you what is the constant of variation here? Is there a constant of variation? When you're making the graph, remember a graph has x and y axes like this, where our x-axis is going to go horizontally and our y-axis goes vertically. And we have our direct variation equation, y equals k times x. Again, you take your y, that shows you how far up and down to go. That takes your x, tells you how far right and left to go. And then your k shows you how much they're changing. What's special about the line y equals kx is I could plug in some values for you, but in the case of time, know that it goes through over 1 up k, over 2 up 2k, etc., etc. And so it goes straight through the origin like that, and I clearly did not make this super straight. I mean, the line is straight, but the points don't lie on it. There we go. It goes like that. Okay. What's important to note about the direct variation equation is that the line passes through the origin. It will always pass through 0, 0. That's this guy right here. Where the axes meet, a direct variation will always go through. And the slope of the line, how its steepness is always going to be k. Okay? So let's just determine without even graphing, is something a direct variation or not? You can tell because it fits the direct variation equation. If it looks like this, it's a direct variation. My hint for you is wherever you see direct variation, rewrite this equation. Y equals kx. Rewrite it here, rewrite it in your instructions, and put it right next to the problem. Okay, first we want to get this problem to look like this one. The easiest way is to solve for y. So that's what I'm going to do. I'm going to solve for y. In order to get y all by itself, I'm going to divide by 7 on both sides. Those 7s are going to cancel out, leaving us with just y equals 2/7 x. Now let's see, does it fit our direct variation pattern? Well, it is a little bit big, so I'm going to make this bigger. We've got an x, we've got a y equals something times x. So yes, that does fit our pattern. Excellent. This is a direct variation. Let's do it again. let's see if this fits our y equals kx pattern. Again, we want to solve for y when we get y all by himself. So our first step here is we're going to subtract 4x from both sides. These will cancel out, sweetums, leaving us with 3y equals negative 4x plus 8. We are still trying to get y all by himself, so we'll divide by 3, divide by 3. Everybody divides by 3. So we get y equals negative 4/3 x plus 8/3. Okay, we've got our y. Oh, I didn't bring him down. Our direct variation equation is right here. Excellent. Does it follow this pattern? We've got y equals some number, in this case negative 4/3, times x. Oh, that's awkward. We've got a third wheel right here. So, nope, this is not a direct variation because it's got a plus something or other. Oh well, we still love and accept this equation. Okay, so that's how to check. Just is it a direct variation? Does it follow y equals kx? Okay, cool. Well, what if we have information and we need to write a direct variation equation? Well, let's copy our y equals kx for a direct variation down here so we know our pattern. And it says, suppose y varies directly, oh, that's a good sign, varies directly with x, and y equals 30, oops, wrong thing, y equals 35 when x equals 5. What is the value of y when x equals 9? Well, what do we know? We know it's a direct variation because it says varies directly. So cool. Okay, cool. And also, what else do we know? Well, we know the problem. We know the values of y and we know the values of x. We know that y is 35, so I'm going to get rid of my y and say, haha, 35. And we know that x is 5. So I'm going to say, ha, by x, you are now 5. Super. This will allow us to find what our constant of variation is. So in order to find our constant of variation, I'm going to rewrite this guy real quick. I don't like the k times 5. I would rather see it as 5 times k. Because in doing that, that helps me see that, oh, hey, I just need to, if I want to get k by itself, I just need to divide by 5. So I'll divide by 5 on both sides. And 35 divided by 5, well, that's 7. That works out so nice. Who made this problem? K is 7. So I now know my constant of variation. Now that I've got my constant of variation, I can plug him back into my original equation. So instead of k, we've got 7. Super! And then it asks us, hey, what is y when x equals 9? Well, we know x equals 9. So I'm going to plug that 9 in for my x as well. So instead of x, we've got 9. This is not 79. This is 7 times 9. 7 times 9 is 63. So hey, y equals 63. Cool. We've got it. Cool, huh? Okay, that's great, but when are we going to use this in real life? Well, for your next trip to Mars, I don't know, we just want it to be fun, but there are plenty of different applications. Here we're going to just go to outer space. So let's say you want to compare your weight on Mars with your weight on Earth. You already know your weight on Earth. That's easy to find. We're going to make that our independent variable. We're going to make our weight on Mars our dependent variable because we're going to use our earthly weight to calculate our Mars weight. Now, Mars is smaller than Earth, so you're going to weigh less. It has a less gravitational pull than Earth does because Earth is bigger. So we're gonna lose some weight. We're not losing mass, we're losing weight. Anyway, well, you can ask me more about the difference between mass and weight later. So your weight on Mars varies directly. Ooh, varies directly. What do we write? What's a direct variation? y equals kx. Okay, good. With your weight on Earth, which we will use to represent x. This is y. The Curiosity rover, which should be capitalized, but I don't know. Should it be capitalized? Maybe. Who cares? Weighed 2,000 pounds on Earth. Oh, Earth. Earth is an x value. 2,000 pounds on Earth, but only weighed 760 pounds on Mars. What's an equation that relates the weight in pounds on Earth? Weight in pounds on Earth, x, and weight on Mars, I'm assuming still in pounds, y. Okay, so first we know function variation. And by function variation, I mean direct variation. Super. What else do we know? Well, we know the Mars rover didn't change. It's still the same. It's still the same Mars rover. And it weighed 760 pounds on Mars. And it weighed 2,000 pounds on Earth, which is huge. You guys, that's huge. That's like 10 big people. That's like 10 adult people. I always thought like the rover was like a small golf cart. Or like a kayak. But it's way bigger. Anyway, so now I'm just rearranging them because it makes it look better. That's really the only reason. We don't know our constant of variation, but we can figure it out. We have enough information. So by plugging in what we do know, we can figure out what we don't know. And that's basically how all of life works. Just kind of take what you do know and you can figure it out. Okay, if we're solving for k right here, all we need to do is divide by 2,000. And 760 divided by 2,000 is really easy to do if you have a calculator or have done this problem before as you were preparing this lesson. It comes out to 0.38 and the 2,000s cancel out. So, okay. So our constant of variation here is 0.38. If you like fractions as much as I do, you can note that that's equal to 9 over 50. So if you want to work with fractions, you can. We will be working in decimals today. So that's very exciting. All right. Okay. So our weight on Earth, or rather, now we're going to graph it. Oh, I didn't actually make our equation. We got to plug it in. Plug it in, plug it in. Okay, so we're going to replace our K with our 0.38 or 9/50ths. If that floats your boat, launches your rocket, you know, fun space things. Okay, so wait, what did X represent again? We said X represents your weight on Earth. So I'm going to go ahead and label this axis. Weight on Earth. Okay, and then Y represented our weight on Mars. Oh, in pounds, guys. We got to write pounds. If you want to know why we use LB as an abbreviation for pounds, please ask in class. I would love to go over it with you. Don't mind my tech struggles here. Just trying to make it look good because I like to do good work. Anyway. So we label our graph so that we can actually understand what it's all about. And now let's do our math. So what do we know? We know that if we want to find our weight on Mars, then we just plug this information in. So we're going to take whatever our weight on Earth is, and we're going to multiply it by 0.38. All the way down. Okay, so we plug in 0. That's 0. And you know, if you weigh 0 pounds on Earth, you'll weigh 0 pounds on Mars. That makes sense. 0.38 times 50 is 19. Oh my goodness, you guys. Did I say this was 9/50ths? I totally meant 19/50ths. 100% my bad. Oh, hey, fun, easy math. 0.38 times 100 is literally 38. And 0.38 times 150 is 19 plus 38, which is 57. Notice, guys, how I used easy math. How I figured this out was, well, I did the zeros. That's easy. 100 times a decimal is easy. And then to go to 50, I just divided it by 2. And then to go on 50, I added them together. So there's your like A+, how to do math fast trick. Hey, let's plug them in. Okay. So we've got 0, 0. Over 50 up 19. Over 100 up 38. And over 150 up 57. Ta-da! Okay, 57 should be like there. Ta-da, ta-da, ta-da. There's our fun graph. Now you can use this to estimate how much you would weigh. So if you weigh like 125 pounds, this is more like 130 pounds. If you weigh 130 pounds on Earth, you probably weigh 50 pounds on Mars. So you want a nice way to lose weight? Go to outer space. Ha, that was a joke. Okay, anyway. Now we just need to determine from a table, is this a direct variation or isn't it? Hey, direct variation! We gotta bring up our direct variation guy right there. Except, guys, this one isn't too helpful in this case. I mean, it will be fine. It would be fine. But there's a better way. And here's the better way. Let's divide by x on both sides. Because remember, a direct variation just means a ratio, right? We have a common ratio here. So our x's cancel out by, so we get y over x is equal to k. So now all we need to do here is we need to look at this guy and we need to say, hey, what is y over x? And that's literally what we're going to do. We're going to take our y's, we're going to divide them by our x's, and see if we get the same thing. Okay, so here we have 6 divided by 4. We took our y, divided by our x. And 6 over 4 reduces to 3 halves. We're just going to leave it like that. So this gives us whatever k is. Okay, for our next one, we're going to take our y divided by our x. Weep. Looks like a weird snowman. Or a division symbol. That's literally what it is. Okay, anyway. So we've got 12 divided by 8, which reduces to 3 halves. And then finally 15 divided by 10. Oh, hey, that reduces to 3 halves. That's so nice. So yes, this is a direct variation because we have the same constant of variation. Okay. Now, did you get it? Let's find out. So again, you're going to take that same process. You're going to take your y's, boom, and then you're going to divide them all by your x's, and see what you get. Okay, so you need to do that for all of your data values. Actually, you don't even have to do them for all of them. I'll show you why. So we get 3.2 divided by -2, which comes out to -1.6. Sweet. Then you get 2.4 divided by 1. Oh, I know, that's 2.4. And now since these are different, you know they're not the same. So no, it's not. K changes. This is not a direct variation because we have different Ks. So you don't even need to bother to check the last one. You would get 0.4 anyway. So it's like super way different. It's really not a direct variation. So there are 2 ways to determine if something is a direct variation. 1, you say, hey, does it fit this equation? Or 2, does it fit this equation? Because they are the same thing. Okay, yeah. Hey, that's a direct variation. And you know, the number of math problems in your homework varies directly with how much fun you have. That's actually not true. But I hope you do have lots of fun anyway. Have a wonderful time.